Ladies and gentlemen, it's my pleasure to welcome you to the session, the parallel sessions. That was mainly organized by Beat Löffler for sure, but I supported him in selecting some appropriate people. And I'm happy that you are here. And I'm also happy that we have so many speeches in this session, so it will be difficult to survive. But nevertheless, I ask you to keep the time, 12 minutes, plus some discussion, and we will have some time at the end for discussions, but I hope that will not be needed because we will be tired after such a long session. If you have any question, please feel free to ask me. My name is Bert Müller. I'm here in Basel, professor for material science and medicine. And my background is physics. I think we are really interdisciplinary here. And the subject we will deal with is nanotechnology based biomedical sensing and analytics. And the first speech will not given by Mrs. Maria Plodinek, but Philipp Oertle. He has made a PhD with her and is from the same team and knows everything as well as Maria does. So we are looking for your speech. Please, the floor is yours.
Thank you. Welcome, everybody. How can I start the slides? Thanks. Okay. Today I will talk about epithelial cells, epithelia, and how to reconstitute them in vitro, and how we can use in vitro epithelia to recapitulate cancer invasion in vitro. What you see here is a typical epithelium of the human body. It's a mammary duct. You see here nicely this in red the layer of basement membrane, which is like the substrate for all epithelial tissues across the human body, be it in kidney or colon or skin. Then you have the double layer of epithelial cells, which is characteristic for mammary ducts. And here you see a schematic of such a, what we call epithelial microenvironment. So this kind of structure where you have a lumen inside and then a one or multi-layered epithelium and the basement membrane beneath and the stroma outside is used throughout the whole body in most organs that bear some epithelia. The basement membrane here in blue is also first barrier towards cancer. So if you want to go from a benign cancer where the epithelial cells are trapped in the lumen to a malignant stage, you need to get through this basement membrane, and I will talk a bit more about this basement membrane and how you get through. Other than that, the basement membrane is also crucial for development because it is bilayered, it's an asymmetric structure. Epithelial cells only stay with the luminal side, which is rich in laminin, and the stromal cells or fibroblasts, they stay with the outer side of the basement membrane, which is rich in collagen 4. Okay, so to study, the problem is a bit that these basement membranes, there is a lack of basement membranes to study epithelia in vitro. So we use inner limiting membranes, ILMs, from human eyes, which are extracted from the retina. It's like a thin sheet that you can peel off the retina and then use it as a substrate, so you can just flat mount it. And when you seed cells on them, you see that they grow firstly much denser on these native basement membranes as compared to dishes or artificial substrates. When you measure the transepithelial resistance, you see a sharp increase in the resistance, indicating that the cells form a tight barrier. And when you look at different polarity markers, so for example, ZO1, E-caterin, or ATPase, which seal the junctions or the epithelial layer, you find that on this inner limiting membrane, they recapitulate what you find in human tissue, for example, in kidney. We found earlier that, or in 2012, that malignant cells, a hallmark of malignant cells is that they get very soft. So a prime interest of our group is to see if we can also recapitulate the mechanophenotype of these cells in vitro. And this we do using AFM. In AFM, you take a sharp needle or sharp tip, you press into a cell, and by indenting into the cell, you can feel if it's stiff or soft. This is a confocal image of cells. This would be a cantilever, which is used for measuring the stiffness, and you basically make what's called a force map. So you take a lot of measurements, and you end up with a high-resolution map of mechanical properties of cells. In detail, you do this, then you analyze this by recording a force curve on these cells, and from the slope of this curve, and here the contact area between the lever and the cells, you can calculate your E modulus. And it's been shown previously that the substrate stiffness also directs stem cell fate. So if you put stem cells on soft substrates, for instance, they go towards brain cells. If you intermediate stiffness goes to muscle cells, and stiffer substrates go towards bone. So this was only relating to the substrate stiffness. What we could also see in our measurements is here, the black curve is cells cultured on the epithelial side of this basement membrane, that only the right combination of the components, so laminin, so the protein composition of the substrate, combined with the right stiffness, gives you a stable mechanical phenotype over time. If either the stiffness or the composition of the substrate is off, then you get fluctuations in your mechanophenotype of the cells. And the reason for this loss of stability in the mechanophenotype is that you either lack this laminin or integrins. And you see this here is depicts the membrane of a cell, and this here would be the substrate side. And to be able to establish the right cytoskeleton or the right mechanophenotype of a cell, you need this interaction of integrins and laminins in order to organize your cytoskeleton, actin, intermediate filaments, microtubules. And for instance, in many cancers, laminin and integrin are gradually lost in more malignant phases. So we try to recapitulate this with our cells on the inner limiting membranes in vitro, taking blocking antibodies that block either the integrins or the laminin, so you can block either the substrate or the cell. And we find that upon blocking beta integrins, the stiffness of the cells is reduced, which is the same finding that we have in cancer, which also goes together with a loss of integrins in in breast cancer at least. For the laminins, the case is a bit more complicated. There you have a wide array of alpha chains, and depending on what chain you block, you get either an increase or decrease in cell stiffness. So AFM is is only a feeling method, so you feel that something gets softer, but we wanted to corroborate this with confocal microscopy. So here you see from the apical side, so from the top end of the cell to the basal side where it faces the substrate, you see the main components of the cytoskeleton. Here cytokeratin, which makes a cage around the nucleus, which is here depicted in blue, and the actin being more attached to the interface of two cells. And we see that if you block the laminin and cells are stiffening, you see here more cytoskeletal components at the apical site, so at the top end of the cell, where you're actually indenting with the AFM. And also the actin assembles, whereas when you block the integrins, the cells get softer, and you see a shift to the softer part. Okay. And finally, once you've lost integrins and ECM, or the connection between the two cells, here they would be in the lumen. Below is the basement membrane, where we use the ILM, the inner limiting membrane, as in vitro. And once they lose these connections, they have to get through the basement membrane, degrade it in order to metastasize. So we took some more cancerogenic cells or invasive cells, put them on the ILM, and we could see that after months of culture, they are able to break this membrane. We then went on, we teamed up with Daniela Vinjevic and Alexandros Glentis from the Curie Institute. They have a very nice model where they take mesentery, which is like a small, thin basement membrane that keeps the intestine in place and together. It's also a bilayered basement membrane, so it has this asymmetry that I mentioned in the beginning. And what we did was to put cancer-associated fibroblasts from patients on one side of the basement membrane, let them work on the basement membrane while they are subjected to signals from cancer cells, then remove the cancer-associated fibroblasts and put cancer cells there. And what we observed, that you see that here again, cancer cells on one side and fibroblasts on the other side, is that if you give them up to 7 days time, the cancer cells here in green, they start to really go through the basement membrane. And then we did some more AFM experiments. These are again force maps. So you see that after having treated the cells with cancer cells and fibroblasts, you really see holes in this basement membrane, indicating that the cells are going through this membrane. At the same time, you see that there is a decrease in stiffness, so this basement membrane's got a lot softer as well. What is even more interesting is that with this compound here, GM6001, we blocked protease activity, and we find that if you block protease inhibition, which is protease activity, which is usually used to degrade this basement membrane, we still get invasion, indicating that these cancer-associated fibroblasts really need to actively pull on the basement membrane to break it. Whereas with blebistatin, we block actomyosin activity, so the cells cannot pull anymore, you lose this invasion. So the cells need to be able to pull rather than proteolytically degrade basement membrane, at least in this case of the mesentery. And now we want to combine these measurements. So I give you a quick outlook. So yeah, maybe. So what we combine here is the AFMs together with the spinning disk, confocal spinning disk, where we can observe then in real time what we actually do with the cantilever. So here you see a nucleus where we are indenting with a lever into the nucleus. And here you just see a movie where you see the tip going around on the cells in actin, and you see where the force is distributed. Yeah, and then the cool thing is that AFM, same technology, you can also then use to measure on the tissue level. But Marco, in his last talk in this session, will cover more of this. Yeah, thank you, everybody.
Thank you very much. Who is with a question here? Okay, maybe I can ask a question. What's about the cantilevers? I think they play a very important role. So the shape of a tip, as you have shown, might not work because the cells don't like these very sharp tips, I think. And can you comment how to prepare the tips and where you buy the tips?
Actually, we do use considerably sharp cantilevers still, with an opening angle of 20 degrees. We just got them from Bruker, so these are DNPs. And with the last setup that I showed you, with the combined AFM confocal setup, you can actually verify that your tip didn't hurt the cell. So you can see if you go through the cell membrane or not. And if you don't go to very high forces, you can see that you don't hurt this membrane.
Any further question, please?
You showed while indenting your. You can speak up, I guess. Yeah, but you showed when indenting your cantilever, the actin fibers were actively like reacting to it.
Mm-hmm.
So how do you deduce this from any stiffness events, or like do you calculate this in while trying to deduce the stiffness of the cell?
You mean the last video where you see the cantilever going around?
This awesome video, yeah.
Yeah, that's not really about measuring the stiffness in this case, but instead you do more lateral movement to see how far the force spreads in the plane. So you see how stiff it is. So, because in conventional force mapping you can only measure in this direction, whereas now you can also again do what's called friction measurements, and see optically how you pull the things, and from this deduce the stiffness from the optical image.
Okay, thank you very much. Thank you, speaker, again.